All right, guys, welcome. Sorry about the way this week is going. A snow day and then a COVID day. It's just it's a crazy week. So hopefully this video will make things easy for you as far as what's going on with this week. So here we are in week two. This is sixth period's assignment page, but seventh period looks identical. And so these are the last 2 days, if you will. So the 29th and 30th, depending on whether you're remote or in person either day. So this PhET Vector Lab is really important as far as understanding vector addition, and component and resultant vectors and just how they apply with the angle and finding that. So really critical that you spend some time understanding this PhET Vector Lab. The dimensional analysis practice sheet is something that's going to be kind of carried forward. So it doesn't really apply to what we're doing right now, but it's just an ongoing thing that we need to make sure that we're getting that skill down. Okay. So again, these are all the assignments we've had thus far. And these last two right here are what you have due at the end of this week. So make sure you're getting that done. I'm going to come to the classwork. And so the in-person day today is the one I'm doing. And so if you click on this right here, it will take you to this. Okay, so the in-person day, so again, 10:30 or 10:29, depending on which group you are in. And just clicking on what is due today. So when we go back into school, we'll do our This Is Me presentation. So make sure that is ready to go. We're going to do a quick warm-up right now on metric conversions and scientific notation. And that is because you will have your quiz the beginning of next week. Mechanical equilibrium notes are what I'll spend the majority of this video on. There is a note catcher that goes along with it, and I'll show you where to get that in a moment. And then the only thing you'll turn in from today's in-person lesson is this dimensional analysis practice sheet. For the remote day, so yesterday, if you are in the A group, you should have done the PhET Vector Lab 1 through 20. And again, this is super critical that you understand this, and then you can finish up your This Is Me, so it's ready to go beginning of next week. So then again, what's due? Dimensional analysis practice problems and the PhET Vector Lab. And then so here, quick, and I'm going to actually pop down to, well, I'm going to come back to this in just a moment. So these are the metric conversions. I want you to try these out really quickly, and then a couple scientific notation problems. I have them on another slide, which is why I'm going to run through this really quickly. But the mechanical equilibrium notes, there's a note catcher. If you click on this slide and open that slide up, then you can fill that in. And I'm going to click on this and open up the notes, and that they're actually right here. And so this is where I am now, but I'm going to come back to that warm up so I can actually kind of go through this. So I would recommend pausing the video here and just trying these two problems, at least these two, just to make sure you come up with the right answer, because you will have to be able to do this on the quiz. But I'm going to go through it right now. So I have milligrams and I want to get to kilograms. So I have 0.57. So I'm going to start off with that 0.5, and I apologize for my terrible handwriting here. I'm writing with the mouse. Milligrams, and I'm going to convert that to kilograms. So first I'm going to come over here and I'm going to find milli, and I'm going to see that milli means 0.001. So that tells me that 1 milligram is equal to 0.001 grams. Okay. So then my milligrams are going to cancel out. That's why I put this one on the bottom here. And my answer will be in grams, but I need to get to kilograms. So I need to do another conversion factor. So I'm going to find kilo over here, and I'm going to see that kilo means 1,000. So 1 kilogram is equal to 1,000 grams. So 1 kilogram. So my grams are going to cancel out here, and my answer will be in kilograms. So it's 0.57 times 0.001 divided by 1,000. And if I do that, I get 1, 2, 3, 4, 5, 6 zeros, and then 5, 7. Okay. So then I'm going to do the same thing on this bottom one, and I'm going to do it for megameters, and I'm going to go to decameters. So I'm going to start off with 3.6 megameters. And I'm going to come over here and I'm going to see that mega means million. As soon as I find it, it means million. And so 1 megameter equals 1 million. I can write this meters. Okay. The megameters will cancel out. My answer would be in meters, but I want it in decameters. So if I find deca, I see that it means 10. So 1 decameter is equal to 10 meters. I did meters on the bottom because meters is on the top here. Cancel those out. My answer will be in decameters. So I have 3.6 times a million is 3,600,000 divided by 10 is 360,000. Sorry, 1,000. Okay. So that's how we do that. And then scrolling down here, oh, I already have that filled in. But so 3.56, so when we do scientific notation, you just write your non-zero numbers, and then it's your first number, then your decimal. So 3.56 times 10. If the decimal is not written, it's always at the back. And so I went 3, 6, 9, 12 times. So my positive exponent to show a really big number, and 12 times is the number of times I moved my decimal. On this one, my exponent was -7. So I have 5.64 times 10 to the -7th. That -7 tells me that this number is going to be really small. I make it a small number by moving the decimal to the front. To move it 7 times, I'm going to have to put 6 zeros in front of my first number. So 0.000000564. Okay. All right, so then you should have up your note catcher, and I'm going to run through these notes. So this unit is called mechanical equilibrium, and there's not a lot to this unit, but you need to understand vectors and how to draw vectors, how to add vectors, how to get a resultant of 2 component vectors in this unit. So again, that PhET vector simulation is super critical to understand. So first off, we'll be talking about forces throughout the year, and it's pretty important to know what a force is. So a force simply defined is any push or pull. Okay, so any kind of a push or pull. And the other thing that's important here is it's required to cause a change in motion. So without a force, you cannot change the motion of an object. Okay, that is really important to understand. And then it is measured in newtons, okay, in honor of Sir Isaac Newton, who defined forces. And then I'll give you this for quite some time, but eventually you're going to need to know this, that 10 newtons, approximately 10 newtons, it's actually 9.8, is equal to 1 kilogram, which on Earth is equal to 2.2 pounds. I say on Earth because in Earth's gravity, 1 kilogram is 2.2 pounds, okay? And then net force. This is really important to understand as well, that generally speaking, there are more than one forces acting on an object, and those forces can add together or they can cancel out. And so the net force is the sum of all the forces that are acting on an object. So again, this is a special word here, tension. We'll be doing our tension lab beginning of next week. And so tension is a stretching force. Okay, so as something is pulled, that is a tension force. Weight. Weight is something that's really confused often, in that people think that weight is gravity, and it's not gravity. It's the gravitational force, but it is not gravity. Gravity is actually an acceleration. The acceleration of gravity acting on a mass is what gives us weight. Okay. So then over here, vector. And then so you should have been exposed to vectors in that introduction to vectors activity you were supposed to do. And so we should remember that a vector has two things, direction and magnitude. I underlined magnitude here simply because I know going forward, people are going to get confused by this word. I will ask a question like, what is the magnitude of the force such and such? And people will say magnitude, and they don't know what I'm talking about. When I talk about the magnitude, I'm simply talking about the quantity. What number are we talking about? So if we're talking about force, 10 newtons to the west, I don't care about the direction. If I'm talking about magnitude, all I care about is the 10. The 10 in the 10 newtons is the magnitude. Okay. And then, so again, a vector quantity that needs direction and magnitude. So usually I show this quick little video of my favorite supervillain, Vector, who commits crimes with both direction and magnitude. But you don't need to see that right now. You should watch that later on, though. It's cute. So anyway, direction and, again, magnitude, that the quantity that we're talking about. So I want to point out these three vectors right here. So it's critical that as we move forward and start doing what are called free body diagrams and drawing the forces that are acting on an object, that we're cognizant of the length of the arrow that we draw, because the length of the arrow means something. We're talking about the magnitude of it when we draw the length of it. So the direction is pretty clear and straightforward, but the magnitude is going to be the length of the arrow. So when I'm looking at these three vectors, the direction is all the same. The magnitude is quite different. So this is the least magnitude, and this is the greatest magnitude. Examples of vector quantities: force, velocity, acceleration. Excuse me. Scalar quantities. So a scalar is different from a vector in that it doesn't care about direction. It just cares about the magnitude. So examples would be time, speed, and distance. So if you talk about the time, it took 5 hours. You wouldn't talk about the direction of the 5 hours. It just took 5 hours. We're just talking about the magnitude. So then we come to mechanical equilibrium. So there are three states of equilibrium that we'll look at. Today we're just going to look at two, but we have a pretty cool demo that we'll do in class where we look at a third one. But mechanical equilibrium is this state where no physical changes occur. Now, when I talk about physical changes, I'm referring to a change in motion. So you might recall from the very beginning, I said a force is needed to cause a change in motion. If something is in equilibrium, there is no change in motion. That is not to say that there are no forces acting on it. It just means that those forces, if acting on it, are balanced. And we'll look at that in a moment here. So net force equals 0. So if the net force is equal to 0, we'll say it's in equilibrium. Another way of saying net force is to say sigma F. The sum of the forces are equal to 0. Okay, so here's an example, and I'm going to go forward right now into a different page just to show you a better idea of this. And I already drew it out. I'm sorry. But if I look, I can see that these are my three downward, I'm doing terribly here, downward forces that are acting on this system. So the weight of this window washer, the weight of the plank, and the weight of this window washer. Then I have two upward forces, which is the tension in these strings that is holding it up. You're told that the sum of the forces are equal to 0. Well, it turns out that if the forces are in the same direction, we add them together. So that is my total upward force, the resultant of these two component upward forces. And then these downward forces, if I put those side by side, you can see that they subtract out and cancel out completely, if I put that perfectly in there. Okay, so the upward and downward vectors cancel out. And so this system here is in equilibrium. It's in a special kind of equilibrium called static equilibrium, which I'll get to right here. So when I scroll down over to here, I'm going to see that over here, again, the sum of the forces equals 0. And then these two upward arrows that I had, they're what are called the support force. Now, the support force can be referred to also as what's called the normal force. And I would use this term when I talk about something like a book on a table. So normal in the sense of a mathematical term, meaning perpendicular. So I have this table. The force that this table is exerting on the book is perpendicular to the table itself. Okay, so that's why it's called the normal force. So you look at this book and you'll say, well, the weight of the book downward is exactly countered by the upward normal force that the table is giving. This is an equilibrium. If I push my hand on this spring, the spring is being compressed. I'm pushing downward, but the upward force, the tension in the spring, or the push of the spring, if you will, is equal, and in the opposite direction, it is balanced off. So this is also an equilibrium. An upward force is said to be positive, and a downward force is said to be negative. So they subtract out from one another. And we'll look at that a little further down. So here is a critical section. You've got to get this down. You will see this in the rest of physics, that objects at rest, you need to stop right then and say at rest. In physics, that has a very important meaning. At rest tells me right away that the sum of the forces acting on the object are 0. If it is at rest, it's not moving. If it's not moving, it is in what's called static equilibrium. If it's in static equilibrium, the sum of the forces acting on it are 0. This book right here is in static equilibrium. The downward and upward forces are balanced. They equal 0, and therefore it is in static equilibrium. This one here, this is a little bit more confusing. Objects in motion, but at constant velocity. Right there again, code word, constant velocity. That tells me that there is, and remember that velocity is a vector quantity. If it's a vector, it has both magnitude, your speed, and direction. Okay, so if it's traveling at a constant velocity, there is no change in speed or direction. Super important that you understand that. But again, if it's at constant velocity, that tells me that the sum of the forces are 0. It is in equilibrium, a different kind of equilibrium, because this time it's moving. So it's not static equilibrium. This time it is dynamic equilibrium. Okay, so I'm going to look at these three situations right here. So I'm going to start off with Nellie Newton here. Nellie Newton is hanging from this string, which is connected to a scale. If Nellie Newton is not moving, then she's in static equilibrium. If she's in static equilibrium, then the sum of the forces acting on her are 0. I see that she's suspended from a scale here that's reading 300 newtons. If that reading is 300 newtons, that pull upward, the tension in this string is 300 newtons, then her weight is also 300 newtons. So when I come over to this situation, now she's suspended by 2 strings. Well, I know that her downward vector, her downward force, her weight has not changed. That's 300 newtons. So the combined upward force has to be 300 newtons. You'll see that the size of these vectors are split. They're half this size. So that means that each one of these strings is holding half of her weight, therefore 150 newtons each. Okay. So again, that's how we would use static equilibrium. In this situation, this is a free body diagram. It's missing a kind of a couple pieces of critical information. There's actually 4 forces acting on this plane. There is the thrust, the forward push of the plane from the propeller. There is the drag, the air resistance that it's encountering. There's the weight of the plane, which would be a downward vector. And then there is the lift of the plane provided by the wings. That would be an upward vector. Okay. But they're just concentrating on these two right here. And you'll notice that the thrust and the drag are the same length vectors. They're in opposite directions, but they're the same length. Because they're the same length, but in opposite directions, they cancel one another out. The sum of the forces equals 0. I might look at that and say, well, the plane's not moving because they cancel one another out. But in order for this plane to stay in the air, it better be moving. It is moving, but what I know about it is it's moving at a constant velocity. Its speed and direction are not changing. It's traveling at a constant velocity. The thrust and drag are exactly balanced out. This one's a little bit complicated. So this car is going around a corner. If I were to tell you the speed of this car is 10 meters per second all the way around here, and I were to ask, is this car in dynamic equilibrium? Its speed does not change. I would say, no, it is not in dynamic equilibrium. The reason for that, while its speed didn't change, its direction did. It took a force which was caused by the tires turning to give it that change in direction. There was an outward force exerted on this car. There's a net force acting on it to cause a change in motion. The change in motion didn't affect the speed. It did affect the direction. So there is a net force acting on this car. All right, so then to finish up, we're going to just talk about vectors really quickly. So remember that if vectors are in the same direction, we add them together. If they're in opposite directions, we subtract. Okay, so I don't know why this is moved. I should have a couple of vectors right here. There, I moved them down here. Originally, I had a vector here and a vector here. So they were acting on this box. The result of these two component vectors, so we're going to get to that term, components are what make up the result. So the result, this red arrow, is the result of these two components. And so we add these two together to get this vector here. And I had it like this earlier, sorry. This one was acting in this direction. So the result of these two vectors is going to be where I subtract these two. So the result will look like this. So this one will cancel out some of this. So we're left with a smaller force, again, in this direction to the right, but it's a smaller magnitude force. That applies over here, even if they're up and down. I'm going to subtract those two and get a net downward force. These two will add, and then I will subtract from this one. So I'll get a net rightward force for this one. So then that's all fine and good when we're talking about forces in one dimension, that they are just in the same direction, they're aligned. But in 2D, if they're at a different angle to one another, then we need to use what's called the parallelogram rule. So if I have two vectors, two component vectors that are at right angles to one another, and I want to know what the resultant force of these two is, I mean, conceptually, I hope you could look and say, well, if there was an object here and there was an upward push on it and a rightward push on it, it wouldn't move straight up and it wouldn't move directly to the right. It would do some combination of those two. It would move at some angle upward and to the right. Exactly what? Well, that's when we use what's called the parallelogram rule. So in this case, I would draw a line parallel to this one right here, and a line parallel to this one right here, and I would construct a parallelogram. It would be a rectangle in this case. And then I would draw the diagonal of that parallelogram to get my resultant vector. It would look like this. So the resultant, this, comes from these two components. And you'll notice that when I went from here to here and drew the resultant as a solid line, the components turned into dotted lines because they're no longer there. I took those two, combined them to make that resultant vector. It's important that you can kind of see that, okay? So taking the two components to make the resultant vector. Same thing applies here. In this case, I'm going to get a square. I'm going to draw a line here and a line here and draw my my diagonal. And when I do that, my resultant vector will look like this. they're not always going to be perpendicular to one another. So in this case here, it looks a little bit confusing. What do? I draw a line parallel to this one from the end of this going up. I draw a line parallel to this one from the end here going up. And then I'm going to draw a vertical diagonal that's going to look like this. Okay, so my resultant ends up being vertical for these two component vectors. Okay. So then I'm going to come over here and apply that to something. So it's asking how many force vectors are in here. So if I were making a free body diagram on this situation, I would see that, well, Nellie Newton has a downward force, which we would call her weight, F of mg. We'll come to that later. So there's a downward force. And then the dotted line here is showing the resultant upward vector. Okay, so she is in static equilibrium. Her downward force and the resultant upward force are balanced. So the net force acting on her are zero. But where is this resultant coming from? It's coming from the tension in these two strings. Okay. And so we're going to work backwards using the parallelogram rule to find out what the tension in these strings is. Okay. So I'm going to make a parallelogram. So I'm going to take a line like this, and I'm going to draw it parallel right here. And I'm going to draw a line parallel to this one here. And then when I do that, I'm going to see that this parallel to this and this parallel to this gives me a dotted line right there. That is going to be the magnitude of my tension in my strings. Okay, so I'm just working backwards. Instead of going from my components to my resultant, I'm looking at what my resultant is, drawing my parallelogram, and then working back to get my resultant vectors, which is right here and here. So how many forces? There are three. 1, 2, 3. There's the weight and then the two tension forces. Okay. So coming down here, this is an interesting question. What happened here? Nellie Newton's weight didn't change. But if I look at the tension in these strings, there's a lot more tension in the strings here than there was here. Why? What's different? Her weight didn't change. Well, what changed was here we had one angle, here we have a different angle. When you change the angle, you're changing the tension in the string. So you see that if I were to even make a shallower angle here, there'd be even more tension. So the tension increases as this angle gets smaller and smaller, if you will. Okay, so there is going to be greater and greater tension as this angle gets shallower and shallower. Okay, that gets confusing when I apply it here, because when I look over here and I say, which one of these strings would have a greater tension? You might say, well, this is a shallower angle. It must be this one. That's not the case, though, and I'm going to explain that here. So here, both angles were equal. Here, the angles are not equal. So conceptually, I might look at this picture and say, well, which one of these is supporting more of her weight? And I would say, well, if I look here, this one's more vertical. This one's supporting more of her weight. And it is. So this is going to be a greater force. How can I use the parallelogram rule to show that? Well, I could draw a parallelogram. So if I were drawing a parallel line from this one, I would do it right here and draw it right there. If I'm drawing a parallel line from this one, I would draw it right here. Okay, would look like this. So there is my parallelogram. Okay, and then recall from here, when I drew in my forces, I drew it where the ends of my parallelogram were. Well, if I draw that in here, look how long my vertical or my component vector is here compared to this one. So when I fill that in, there is a much greater magnitude of force here than there is here. Okay, and we'll look more at that later on. Last question, if they weigh the same, who is going to break the swing? This person is more likely to break the swing. Why? Half of this person's weight is supported in each line here because it is a vertical one. Exactly half of each of the weight is supported by each string or each rope or chain here. Because this one is at an angle, there is more than half. We don't know exactly what it is, but it is going to be more than half of this person's weight that is supported in this line here. So this one is more likely to break. Okay. All right. So coming back to that, that's it for the notes. Okay. So coming back here, the only other thing I wanted to go over really quickly to make sure you kind of have this idea is this PhET Vector Lab. And so when you do this, again, the importance of this is that you understand vectors, vector addition, and then really get to understand resultant and component vectors. So when you come here, this is where it's going to take you. 1D is going to be like when they're aligned one way or the other. So you subtract out, in this case, or add them. You can play around with this one, but this is where you're going to do most of what you're going to do. So if I click on this, it's going to take you here. And these are your vectors that you can pull in here. So I'm going to pull one in, and I'm just going to put it right there. So this is my vector, okay? And I'm just going to put it right there, and I'm going to make it a nice, easy thing that I can look at here. So I think one important thing to do is click on this right here. And when I do that, it's going to show you the X and Y component of this vector. So if I were looking at it up here, I can see that this right here, this is my resultant vector. It results from an X and Y component right here. So I have my A of X, that's this one, and my A of Y, that's this one. So my A of X is 10 and my A of Y is 10. And I can click on values right here and it will put those values in for me, okay? I can also click on the angle, which is cool. That'll show me that angle right there. And I can adjust this as I want. I can change this and see how changing the Y affects my resultant, and how changing the X affects my result. So I can play around with it like that. I'm going to go back to where I was, though, right there. Not right there, sorry, right here, 10 and 10. And then I'm going to pull on another one, and I'm going to make this one the same, 10 and 10. And so when I did this, the cool thing is what I can also do is I can click on sum. But before I do that, I'm going to kind of show you something here. If you look at it in a 1D way, if I look at 1D, my X components, I have, like I say, a 10 Newton force and a 10 Newton force in the X direction. Well, you might say, well, I remember that I add them in that case, and you do. So in the X direction, the result of these two should be 20 Newtons in the X direction, and it also should be 10 and 10, which is 20 degrees in the Y direction. And then if I were to look at it, I would say, well, and then the resultant, this arrow right here, should be 28.2. Okay. And so if I click on sum, let me move this over. I'm going to put that one just right there. And I'm going to put this one right here. And you see it's 28.3, which is not identical. And that's because of rounding here. So it just rounded off here to get the 14.1, and it didn't round as much here. But you do see this is 20 and this is 20. And that comes from 10 and 10 and 10 and 10. And so to show you that, and also notice that the angle here is the same. So here's a quick thought question for you. If I were to change this vector right here, if I were to decrease the angle, would that affect this? If I decrease it here, will it affect this? And hopefully you see that it will. It should, if I decrease this angle, it should decrease this angle, okay? And so I'm going to do that right now. And it did. It changed the angle. This one didn't change, but I'm adding this one to this one right now, and I can see that I get a different angle, and I get different magnitudes. Look, it's still 10 and 10 here, which is my 20, but now it's my 10 and 6, which is 16, which gives me a different result. And we're going to come back to our Pythagorean theorem and talk about a squared plus b squared equals c squared. But I just want to kind of see visually what happens here. If I now decrease this one, you can see I changed the angle again, and I changed everything. And as I change any of these, it affects this resultant vector as well. So I want you to play around with that and kind of get a good understanding of that as you move forward, because we're going to do a lot with this, okay? So really critical that you get that. Coming back really quickly, the only other thing that you need to do is the dimensional analysis practice problems. If you're in period 6, you could click on this. If you're in period 7, you could click on this, or just from our period 6 or period 7, you could click on it right here and it'll take you to the same place. And the only other thing that you need to do is the attendance form, which again will always be the last page of our presentation. So because we're not in person today, the attendance form is right here. So please get that completed. Okay. I hope that this video is helpful and that this doesn't take you too long and that you have a great weekend. But if you have any questions, please know that you can go on Zoom if today is Friday, and I will certainly answer any questions that you have. So have a great weekend, and I will see you guys on Monday.